Hey HMS modelers, this video is a recording of a presentation which was made on October 14th, 2021 by two engineers from the U.S. Army Corps of Engineers, Garrett Blomstrand and Brett Hultgren, both of whom are from the St. Paul district. Within this presentation, Garrett and Brett discuss how to import and use gridded boundary condition data within HEC HMS. They also discuss the use of the new Normalizer utility, which can be used to adjust grid cell values in one grid with information from another grid. This presentation was made to the U.S. Army Corps of Engineers, Mississippi Valley Division, Hydrology, Statistics, and Risk Subcop. Enjoy!
So I want to welcome our speakers today. Garrett Blomstrand. He is a hydraulic engineer. He's been working with the St. Paul district for over 9 years. He's got statistical hydrology experience, hydrologic analysis and modeling, hydraulic modeling, climate assessments, reservoir modeling. And so he's been doing a variety of types of projects in the St. Paul district. He got his bachelor's in civil engineering from North Dakota State University and a master's degree in civil engineering from the University of Minnesota. He's also a registered engineer in Minnesota. And Brett Hultgren, who has also been working on this presentation for you to do today, is in his 5th year with the St. Paul district in the Hydrologic Engineering Center and section, and most of his time recently has been spent as a lead ResSim modeler for a very interesting study in the northern part of the St. Paul district on the Souris River watershed, which crosses between the United States and Canada. Very interesting. He's also experienced in HMS and RAS and really has a lot of wealth to bring to studies. So he's also interested in statistical hydrology and SWIMS and data analysis and those are. And so we've got two great people as your presenters for today. With that, I'll just mention I am recording this webinar. I will be pulling off an attendee list and sending out PDH certificates after the presentation. So with that, I will hand the presentation off to Garrett, and I'll put myself on mute. If you have any questions to ask the presenters, please use the chat function, and we will get to them a little later in the presentation, or I guess if Garrett and Brett feel they see one pop up and they want to address right away, I'll leave that up to you. Thanks, Garrett.
Great. Can everybody see my screen? If you want to put some...
I can see it. Yep.
Okay, great. Like Ann mentioned, my name is Garrett Blomstrand. I'm a hydraulic engineer with the Corps of Engineers St. Paul District. Brett, do you want to introduce yourself too?
Yeah, sure. Garrett already said my name. It's Brett. I'm a human male, 5'11", and I do the same thing Garrett does pretty much.
Yeah, so today the St. Paul District had kind of partnered with HEC to do some software testing and develop some tutorials on some of the new features in HEC HMS. And so today we're going to discuss some of the new import features for gridded data, as well as a normalizer utility for correcting gridded data. So the prevalence and availability of gridded data like temperature, precipitation, certain snow data has increased a lot over the past 2 decades. And a challenge when working with this data is that it often comes in a wide variety of different file formats that can be tricky to process into HEC DSS format that can actually be used in HEC HMS. This often requires a lot of manual pre-processing outside of HMS before the data can actually be utilized within HMS, which is pretty time intensive. So this presentation will focus on the new gridded data import wizard, which can be used to import a variety of different gridded data sets into HEC HMS, as well as the normalizer utility, which can be used to modify or correct a gridded data set based on other known gridded data. And these tools really increase the functionality of working with gridded data and result in some significant time savings and really streamline the process of getting gridded data into your model. Why do we care about data, gridded data, and being able to manipulate gridded data? Well, for most of our hydrologic models, gridded data forms the inputs or boundary conditions to the model. And you really can't create a useful hydrologic model with poor quality data. There's that old expression, you put garbage in, you get garbage out. And that's true with hydrologic models too. If you don't have good precipitation data or other hydrologic variables you're trying to capture, it's going to be difficult to put together a useful hydrologic model that others can use, or it can help inform your study. So gridded data is great because it's widely available, and which makes it really easy to obtain and use. And it also provides excellent spatial and temporal resolution for hydrologic modeling studies. Gridded data is also available for many different types of hydrologic variables like precipitation, or sometimes snow, or temperature grids, or evapotranspiration grids. But not all gridded data sets are created equal, and event-specific and site-specific factors can sometimes influence the quality of the data. So on this screen here, the plot on the left shows runoff results from a simulation using raw input precipitation data to a hydrologic model. The blue line is the simulation, and the black line is the actual observed data. So in digging into this more, what we realized here was that we actually have pretty high confidence in the parameters that were used in this model, but for some reason, we cannot get enough runoff. Now, the two approaches here are you could adjust parameters in your model until you get a fit between the simulated and observed. But in this particular case, we suspect something is wrong with the precipitation data we're using. So if we adjust those model parameters so that these two on the left match, we're probably not coming up with good, reasonable parameter estimates for our watershed. So a more appropriate approach would be to look at other sources of information in the watershed and see how we can use that to augment it to come up with a better estimate of our input precipitation or our model boundary condition. So the image on the right shows the end result of what Brett and I are going to talk about in this presentation and how to do that. So just a note on the accuracy of gridded data. So engineers always need to review gridded data that they're using for accuracy to ensure it meets the needs of their study. A good example is gridded precipitation measurements using radar are widely available and commonly influenced by a lot of different factors. Some of those factors are listed on the lower left hand of the screen here. One of the most common factors that can influence radar measurements is simply just beam blockage. Something gets in the way of the radar beam, which produces an erroneous measurement. A good example of this is in mountainous regions where you have orographic effects. You might have rainfall on one side of a mountain, but not on the other side of a mountain. And so the side of the mountain that didn't get rain, if there was a radar station there, it might not pick up that storm. I tried to look for some other fun and interesting examples of things that can cause issues with radar. And you should be able to see an image here, and you can see a scatter. That's actually caused by a wind farm. So like in this case, this radar station has a wind farm within its line of sight, and the beam blockage attenuates the strength of the radar beam and impacts the data well beyond the wind farm, causing the shadows and spikes in the data throughout the entire range of the radar. Similarly, this is what bats look like when they're picked up on radar and you're trying to measure precipitation data. And then also migratory waterfowl like ducks and geese. You can actually see like the V formations of them flying south. So while these examples are a little less common and a little more fun, the whole point is anytime you're working with radar data, whether you're in a mountainous region or not, you have to assess that data by comparing it to other sources to make sure that it's reasonable and defensible and accurate enough for your study. So gridded data is usually available in different sources from different agencies and in different file formats. The list on the right-hand side of the slide illustrates the types of data which are commonly represented in gridded format within HEC HMS. In popular precipitation data sets, which is what we're going to kind of focus on for this presentation, even though gridded data can encompass more variables, you can usually obtain those from your local National Weather Service River Forecast Center, your district office, other government agencies, and sometimes universities put out that information as well. Just a note, the Corps of Engineers is in the process of setting up Cumulus, which is a repository for easy-to-access gridded data sources. It's currently under construction, but it's coming along nicely. And a goal for Cumulus is to be a one-stop shop for common types of gridded data. So I included a link to Cumulus here on this slide so you can kind of check up on its progress and look at potentially some information you can use for your studies. So the HMS team at the Hydrologic Center, kind of led by Tom Brower and Mike Bartels, recently developed a gridded data import wizard, which has the capability to import gridded data from a variety of different file formats. It processes the data and easily converts it into a DSS file that can be used in HEC HMS for performing hydrologic simulations. Some of the currently recognized file types and extensions that can be imported and used within the HEC HMS Gridded Data Import Wizard are listed in the lower left-hand side of this slide. I can't stress this enough. This new tool dramatically simplifies the process of getting gridded precipitation data or any gridded data into HEC HMS. And so now we're going to switch from the presentation to a demonstration of how to simply import gridded data. So let me know if you cannot see my screen. There should be a colorful HMS model of the Sonoma Creek watershed. So this was a model built by Mike and Tom at HEC. It's just a simple rainfall runoff model with one subbasin. And to start this model, we adopted National Weather Service Stage 4 NEXRAD gridded data. And we used that as our initial precipitation input. So for the purpose of this example, we assumed that we'd calibrated this model before, and we'd run the simulation to look at how well our simulated results match our observed results. And using the NEXRAD Stage 4 data, you get a hydrograph like this. So this is the example that I showed earlier in the presentation. You can see that overall, we're matching the timing and the hydrograph shape of the observed hydrograph really well. So the simulated is in blue and the black is the observed, but we don't have anywhere near the magnitude and flow. And like we discussed, the two approaches you can use are to go back and consider recalibrating. But if you think you've got pretty good estimates for your parameters, you should take a look at the precipitation data and see if maybe that's the issue, because you don't want to create a model that has essentially bad parameter values in it. So that's what we suspected in this case. So that Stage 4 NEXRAD data is hourly data, and it's generally pretty good. But to supplement that and look at the amount of volume that we think the storm is, I'm going to use PRISM data set. PRISM is from Oregon State University. It's a 4-kilometer grid for the entire United States. And it's just a daily rainfall grid with daily rainfall totals for the entire nation. And it's nice because it's a heavily quality controlled product. And so it goes through some pretty good QC procedures, and then actual humans look at PRISM before posting it. So it's generally a fairly reliable gridded data source if you're just trying to look at how much total precipitation occurred over a given time period. So I already went ahead and I downloaded the ASCII files for the simulation period that we're looking at right here and put them in a folder. So what I'm going to do is I'm going to import those and run them in HEC HMS. So to get that data into HMS, all you need to do is go File, Import, Gridded Data. And this will launch the Gridded Data Import Wizard. So first, you just need to select the files that you want to import. So we'll navigate to that folder. And I've got my PRISM data stored right here. If you hit Control-A, you'll select everything. And then this brings all the ASCII files in for import. Click Next. Some gridded data sets can have a couple different variables. In this case, there's only one, this PPT, and that's basically daily total precipitation. So I'm going to bring that over here. This window is going to specify the variable I want to import. And then you'll have some options that you can fill out to simplify the process. So clipping data source, like I mentioned, PRISM data covers just about the entire continental United States. And this is a pretty small model. We do not want to create a DSS file that has rainfall data for the entire continent, or at least the United States portion. So I have already taken a shapefile of my subbasin outline, and I have buffered it by about 1 mile. So I'm going to use that to clip the data upon import. So I go to the GIS folder that I'd set up. And the Sonoma buffer shapefile is a 1 mile buffer around the watershed that I'm interested in. I click Open. Target WKT, well-known text. This specifies the coordinate system that I'm going to be working in and that the data is going to be written out to. I'm going to stick with a standard hydrologic grid because that's what I was using for this study. And then target cell size. So you have the option of changing what the target cell size is. Generally, it's recommended that your target cell size should be greater than or equal to the original data source. In this case, I believe the PRISM data is a 4-kilometer grid, but I'm just going to use the 2,000-meter grid to be consistent with what the Stage 4 NEXRAD data was. This shouldn't cause any issues because we're using a bilinear sampling method, so it's just going to give me smaller cell sizes with the same values. And then I'll click Next, and you have to specify where you would like this information to be saved. So since I want this to travel with the model, I'm going to my model directory in my data folder. I'll call this HHC prism.dss for this HHC presentation that we're doing. Now it's going to ask you for some details about your data. So I'm going to put SHG so people know I'm using the standard hydrologic grid. I'm going to put Sonoma. because that's the watershed I'm using the data for. And then I like in the F part to put where I got the data from. So I'm going to type prism. And now you just click next and it begins the import process. Generally, this process goes very fast. And obviously, if you have a much larger watershed and you're bringing in more data, it might take a little bit longer. But I've never had this process run for more than 10 or 15 seconds. Okay. So when that import's complete, that DSS file is created and it's ready for use. So now if we run a simulation, we just need to set up an appropriate gridded data item in HEC HMS, as well as a meteorologic model, and then create a simulation. So in my components bar, go to grid data manager. I'm going to create a new one. I'm going to call it, I'm going to skip giving it a description, but if you're doing an actual study, make sure you give it a good description. Then you can access that source that you just created here, HHC Prism, and you need to select the DSS file name and path name associated with that data set. So I'm in my data folder that I created, and I have this HHC Prism data set. And this is the imported Prism data in DSS format that we just did. And then you just need to select one row from that DSS file. So I'm just going to select the top row there and click Save. Then you just need to start up and create a meteorologic model. So I'm going to do HHC Prism Met. Again, provide a detailed description for your study. Then you just need to configure your meteorologic model. So I've got this model here. Precipitation method, by default, it's specified heliograph. I need to change that to gridded precipitation. And replace missing abort compute. That'll just allow the simulation to keep going. And just don't forget to come to this basin tab and select yes for the subbasin that you want to use the precipitation data with. Otherwise, HMS will not work. Then we can come down to the gridded precipitation here and select the grid that we created. So I want to use that HHC Prism grid. So it should be good to go there. Now I just need to create a simulation run. So I'll give it a name. I'm going to use the same basin model, which is this one, as the original simulation. You need to select your meteorologic model. So I select the Prism one that I just created. And then control specifications. These are the control specifications that were set up for the original run, and I'd like to use those. So once those are all set up, all you need to do is run the model. And it's a small watershed in HMS, so it runs nice and fast. And I can take a look at the outflow hydrograph there. So we're going to switch back to the presentation because I have some visuals to talk about this, but you see that this also isn't a very good representation of the overall rainfall runoff that we actually observed here in black. So one thing I'm curious about, for my preliminary investigation in that first model run using NexRad stage 4 data, I noted that I had a lot of trouble getting enough volume of runoff to match the observed data. And so what I'm looking at here are cumulative precipitation depth mass curves for the Prism data set and the stage 4 data. And you can see that I had just under 6 inches of rainfall with the stage 4 data and under 13 inches of rainfall for the Prism data. But there's quite a difference in cumulative precip between these two measurements. So upon further investigation, I'm pretty confident that this stage 4 data probably missed some of the rainfall or didn't get the correct measurement at the correct time. So these two images on the left are the rainfall runoff results using the stage 4 hourly NexRad data, and on the right using the daily Prism data. So you can see that from that previous slide, there's a lot more volume with the Prism data than there is with the hourly stage 4 NexRad data. But the nice thing about this stage 4 NexRad data is that since it's hourly, I get a really good idea of what the storm pattern looks like. I know the temporal distribution of the rainfall hydrographs. And these match the runoff response pretty well. Like I'm matching the timing on this initial peak really well and the timing on this second peak very well. It's just the volume. So our question is, we have pretty high confidence in the total amount of rainfall captured by the Prism data, and we actually have pretty good confidence in how that rainfall is distributed on an hourly basis from the stage 4 data. So how could we combine and leverage information from both of these sources to get a good idea of what the actual precipitation time series should be for our modeling purposes? And that's what my colleague Brett is going to talk about.
Good thing there is a tool specifically designed for that purpose. So it's called the Normalizer tool, and it's available in HMS 4.9 and above. The purpose is we want to find some way to combine these two data sets. We want to create a data set that captures the temporal variability or timing of one gridded data source while capturing the volume of another source. So for example, like what Garrett was talking about, we've got hourly stage 4 data, daily prism data. The hourly data captures the temporal variation well, but it underestimates the volume. And the daily prism data captures the volume, but the time step's too big, so it can't capture the timing of the flood peak. So basically all the Normalizer tool is doing is you're going to take all of the grid cells in your stage 4 data, your hourly data, we'll call that data the source, so the source grids. You take all of your source grids and you multiply them by some factor so that when you accumulate all the volume, it equals the volume of your prism data, or in this case, we'll call it the normal grids. So I'll show those two plots that Garrett showed before, our hourly data and then our prism data. And like I said before, all we're doing is we're adjusting the magnitude of each of our grid cells in the stage 4 data, so that when we add up the volume, it equals the volume of the prism grids. So if we look at our cumulative precipitation, before we do our normalization, this is the same plot that Garrett had shown before. We basically want to find some way to move this stage 4 line, this cyan line. We want to move it up so it matches the prism line, or the pink dashed line. So after we run the normalization, or the normalizer tool, we come up with our normalized grid. This is what our cumulative volume of that grid is going to look like. So you see it has a similar shape to the stage 4 grid, but the magnitude is increased. And you see that it basically intersects the pink line at in 24-hour intervals. And the reason why it's intersecting the pink line in 24-hour intervals is because we have chosen a 24-hour normalization interval when we do the normalizer tool. I'll get into that in just a second. So here's the normalizer tool equation. It's pretty simple. You just got your corrected precipitation on the left side. You've got your source precipitation on the right side, and then you're multiplying your source precipitation by some factor or some ratio. And it's just a ratio of your cumulative volume of whatever your normal grid was. In this case, the normal grid is the prism grid. So we're taking the volume of the prism grid, dividing it by the volume of our source grid, and then multiplying that by whatever precipitation we had in our source grid. And it's important to note that we're doing this over some time interval. So if we want to compute the cumulative volume of something, we have to do it over a certain amount of time. So that is called the normalization interval. Just got a few simple examples of how the computation actually works. So let's say we've got pretty much the simplest example we can have. We've got two grids that they only consist of a single grid cell. Your source grid it's got 12-hour grids, and your normal grid has 24-hour grids. And you want to have a normalization interval of 1 day. So in that 1 day, you've got one normal grid and you've got two source grids. All you're doing is you are taking the cumulative volume of your normal grid, which in this case is 10, putting that in the numerator, and then you're dividing by the cumulative volume of your source grid, which in this case is 3 plus 5, or 8. And then you're multiplying it by whatever the value was of your source grid at that time step. So in the first time step, 0 to 12 hours, it's 3. Second time step, 12 to 24 is 5. So you see that we have a distribution of rainfall over time of 38% in the first 12 hours, and then 60% fell in the second 12 hours. And in our normalized grid, we have that same distribution. So our magnitudes have increased so that when we add them together, they equal 10. equal to our normal grids, but we're keeping the same distribution of 38%, 62%. Another example, this time we're going to have a normalization interval of 2 days. So all we're doing is we're adding extra grids to accumulate over. So now instead of just doing the 1 grid for the normal grid, we've got 2 grids of our normal grid. So we're adding them together, putting them in the numerator, and dividing by the cumulative volume of all of our source grids. Now, what happens if one of our source cells doesn't have any data? Well, if one of the source grids doesn't have any data, then the normalized grid is also going to have no data for that time step. And then the normalized grid is just going to adopt the source value for the other time step. If the normal cell has no grid, so if your normal grid has no data, then you basically just ignore the normalization computation and you just accept whatever was in the source grid. So if you have instances of no data, that's in either of your grid sets, that's one way that you can get some error to be introduced into your normalized grid, because those volumes won't quite match up how you want them to. And let's jump into a little bit of a demo just so I can show you where this tool is in HMS. So this is the same model that Garrett was working with. I already have my PRISM data and stage 4 data in here because I've used the gridded import tool and got those into a DSS format that HMS can work with. So now I want to use the normalizer tool, which is in the tools options. I go to tools, I go down to data, I've got the normalizer tool. Select normalizer, you get this wizard to pop up. All I have to do is I have to select my source file. The source file in this case is the stage 4 data, the data that I want to normalize. And I'll navigate to it, select the stage 4, open it, and I get all my grids to pop up. So I know, because I've looked at my data first, I know that the PRISM data starts at noon each day. So it doesn't start at time 0, it starts at time 12. So I'm going to select time 12 to be where I start my selection of my source data. Basically, I'm selecting the grids that I want to go into my normalized grids. So I'm going to pick December 25th, starting at noon, and I'll just go all the way to the end and end at January 10th, also at noon. Slide those over to the right, and I'll hit next. And then I'll select my, which will be my PRISM data, open that up, and I'll select the same time interval. So December 25th at 12 to January 10th, 12. Slide that over to the right, I'll hit next. And now I have to select my normalization period. To tell the wizard where I'm starting at, I'm going to say I'm starting 12/25, 2005, starting it at noon, and I'm going to go to January 10, 2006. And I'll just select a normalization interval of 1 day. I'll go into more detail of how to choose this normalization interval later on, but for now I'm just going to do 1 day. Do it next, and then I have to choose a destination. I'm not going to worry about where I put it right now. For this demo, I'll just put it on my desktop. And I'm also not going to worry about assigning any of my part names, but if you were doing this for an actual project, be specific with what your part names are. Let's hit next. It'll process the data. This, like the gridded import tool, this goes pretty quick. And I'm not sure if this has been, I'm working with the alpha version of HMS right now, so I'm not sure if this has been fixed in a new version, but with the version I have right now, it still says processing, but once it gets to the end, it's done. I'll hit close. And now if I go, I can set up a new simulation, like Garrett had shown before, and I can run it using my corrected data. I've already got it in here from when I did this before. So if I go back to the presentation, let's talk about selecting a normalization interval. So for this demo I just did, I chose 1 day. And it ended up working out all right because the storm event that was being modeled was shorter than 24 hours. And we had consistent rainfall in both of the precipitation grids, the PRISM grid and stage 4 grid. We had consistent rainfall throughout. But for larger models with longer simulations, it's important not to select a normalization interval that's too small because it can lead to errors. For example, here is a subbasin. This is showing some simulation results for a subbasin in the Truckee River, an HMS model of the Truckee River Basin, which is a much larger basin. It's got a lot of subbasins, and the simulation time is quite long. It's multiple months. And here I used a 1-day normalization interval, and this is the HIETA graph for this subbasin. You can see the black stair line is the PRISM data. The cyan line is the original stage 4 data, and then the dark blue line is the my first crack at developing a normalized grid. And I see that I've got this error on January 5th. So they've got this huge jump in precipitation, which it's pretty clear that there shouldn't be. Now, there's really no reason why it should just jump up, get almost 7/10 of precip in 1 hour on January 5th. So let's talk about a couple of reasons why we can get error in grids. So one reason could be due to zero values. So if you have your source grids and they all have zero precipitation in them, it doesn't matter what your normal grids say. Your normalized grids are going to have zero precipitation for those time intervals because you're multiplying by zero. It's the same deal if you have zeros in your normal grid. So if you have normal grids of zero, it doesn't matter what your source grids are, but since you're multiplying by zero, your normal grids are also going to be zero. And so this can throw off your cumulative volumes a bit. Another way you can get error is timing differences. So here is that same subbasin in the Truckee River model. I'm just showing the PRISM data and the raw stage 4 data. So if I look at my 1-day interval, here I've got 1 day where the cumulative volume for this 1-day time step for the PRISM data is significant. But if I look at all the volume that fell for the stage 4 data, it's almost nothing. So I'm going to, the normalization computation that goes into this is going to really ratchet up that stage 4 data for this period because it thinks it has to increase it by a ton to reach that cumulative volume of the PRISM data. That's why I get that huge spike in rainfall over this 1 hour on January 5th. If I go to a 5-day interval, a 5-day interval captures this entire rainfall event. So since all the rain that fell during this event in the PRISM data, I'm comparing all the rain that fell during this event in the PRISM data to all the rain that fell during the event for the stage 4 data. So I'm not going to have these instances where I've got a ton of rainfall that fell in my PRISM grid and not a lot of rain that fell in my stage 4 grid. And each of these time steps is going to be multiplied by the same ratio. So if I compare the results of using a 1-day normalization interval versus a 5-day interval, I can see that on the right, where I use a 5-day interval, my precipitation looks a lot better. I've got pretty evenly distributed increase in precipitation. It follows the same shape as my original grid without having these big spikes or apparent errors. So a few tips for using the Normalizer tool. The first is that your two grids that you are using in the tool need to be essentially exactly the same. The only difference can be the actual values of the grid cells. So things like grid type, your data units, your data type, the extents of the grids, the cell size, spatial reference, all of that needs to be the same. And you can look in and see if all this stuff is the same in DSS. So if you go to DSS, you right-click on one of your grid, go to grid info. You can see all of these parameters. And essentially everything in the red box in both of the grids needs to be exactly the same. So in this case, we've got prism on the right, stage 4 on the left, and each of these parameters is the same in both grids. So essentially that means they sit right on top of each other, and each cell is exactly the same. The only difference is the amount of precipitation that's actually recorded in each cell. Another thing to keep in mind is to make sure that your time periods for your source and normal grids match. So if your normal grid start at time 1200, make your source grid selection also start at 1200. This is essential because if you are asked to specify your normalization for the start and end time for your normalized grid in the wizard, just keep that in mind. Some grids can start and end at different time periods, and you want to make sure that you are, when you're trying to create your normalized grid, you are your normal grid and your source grid are basically lining up precisely. And here I've just got a screenshot of where when I did this back in the demo. So we've got the prism data on the bottom starts at time 1200. So when I selected my source grids, I also made them start at 1200. And then the third tip is to make sure you have a long enough normalization interval. So hopefully that was clear. A good rule of thumb is to pick an interval that's equal to the length of your simulation. If you're doing an event-based model like the Sonoma Creek model, if you've got longer time frames like months or years, you could do weekly, monthly, yearly normalization interval. It really just depends on your preference and also what sort of data you're working with. So if there's maybe there's some sort of reason why maybe the quality of your normal grid changes over time, or for some reason you don't want to include certain time periods in your normalized grid. I think it's better to err on the side of it being too long than too short, but ultimately it's up to you. And a lot of times whether you pick a weekly interval or a monthly interval, your results can be very similar. So you might just have to try one, and if it looks like it's not giving you good grids, you try a longer one. That's about the end of the presentation. We've just got some links you can go to learn more about the Grid Data Import Wizard or the Normalizer tool. HEC has got a lot of great tutorials on their website. There's also a YouTube video you can watch. Also here we put in the link to the Prism data on Oregon State's website. And then for the Normalizer utility, there are a couple different tutorials with that on HEC's website as well. And time for questions. I'm going to stop sharing my screen and go check out the chat, see if there's any in there.
Great job, Garrett and Brett. I think there were a couple that popped up, but they've been answered in the intervening time. I guess Garrett responded to a question about availability of Prism for Puerto Rico, since some of our work for other districts has kind of reached out to that region, and appears to be data there. I guess along that same line, my question to you, maybe Garrett, is when you select these PRISM grids, are they by default for the whole United States, or do you download pieces more like related to your region or HUC2 or something of the country?
Yeah, for the examples that we were working with to get the daily data, you're getting the entire data set. So you're getting either .bil files or ASCII files, .asc, and you do want to clip those because otherwise you end up with a really large DSS file within your HMS model, which is just cumbersome and has a lot of extraneous information that you don't need.
So does each ASCII grid come down for that one particular day? You're downloading by day for the whole United States then, right?
Yeah, exactly. So you get one ASCII file for a 24-hour period in the examples presented here. And PRISM does have some normalized data over longer time periods, but we were primarily using that daily data. So you get one file for one day.
Okay, so you'd want to go in with a good idea of the period that you're really questioning. You know, you wouldn't be downloading a year's worth of data just for the sake of comparing things. You definitely want to target your window of concern.
Yeah, and in PRISM, you specify which month you download. So you'll download basically a month of data at a time. So it's actually pretty quick.
Great. We had a question here about data checking. The idea if you could compare the observed runoff volume to the precipitation volume, that might help to kind of shake out if you've got a problem with your data or not. And Tom responded. I guess, Tom, I'll let you maybe verbalize if you can hop on or turn on your mic.
Yeah. Hopefully you can hear me. Yeah, that's a good thought, doing that data check. I guess in my response, I just said you would have to incorporate a little bit of information about, where is the observed flow location, and then for the precip portion, you'd have to do area upstream of the observed flow location to calculate that volume. So it makes sense as a check. It might be because you're going to do all of that over the simulation. It might make sense just to do that towards the end after you've already done that, and then give an error warning to the user. That might be in there. I am not sure, though. I'd have to check it. I've definitely seen, because I like a lot of us, the notes and warnings kind of get lost on us. We just look for those error messages. So it could be in there. I'm not sure, but I've definitely seen, if you go to any observed flow location and you look at that summary table in HMS, the element summary table, it should show computed versus observed volume. And if your total precip is ever less than your runoff, then you have a volume issue. If your total precip is greater than your runoff, that's good. And at that point, you're probably working with loss rates to get the volumes to rectify. If the total precip and the runoff is like very close, and you have losses that are, don't make sense, like Garrett pointed out in that Sonoma Creek example, he was confident in his parameters, but the volumes didn't add up, then it's probably time to go inspect the precip data again.
Is there a lot of opportunities for uncertainties in your model, whether it's a rating curve or a goodness of a gauge as far as its accuracy and all those pieces too? So I guess you just kind of have to evaluate all of the sources of data and see if it's something that persists from point to point across gauges in the basin, if you're lucky enough to have more than one gauge for your calibration, and take a look at it piecewise. Yeah, but there are some tools in HMS, like you said, at the junctions or sub-basin level to take a look at the output summary and the quick computations that HMS does right now. Any other questions? I guess I have one about, so sometimes in some watersheds, we're so lucky to have point precipitation gauges, whether it's one of our projects or city gauges or something, or even NCDC gauges. If you've got point precipitation depths, it sounds like you probably need to translate that into a series of grids for each of the time steps of the precipitation. Is there a way to do that in HMS now, or is that still a process you would do in a GIS program?
Yeah, I guess the traditional program for doing that would be Gauge Interp, but there is a current work effort to add interpolation capability directly in HMS. So you would start with a number of different precip gauges, or we're interpolating all meteorology, actually. We're setting it up to be generalized, so it could be things like temperature as well. But you'll specify your gauges, and then HMS will do the interpolation for you. And I think the way we've done it is that's a pre-processing step, so it'll go through, interpolate all your grids, and then it will pick up with the simulation. And those grids will remain cached unless something changes in your configuration. And then obviously if there's a number of different things that could change, and we'd have to invalidate that cache and recreate the grids. But it's pretty exciting. I've seen some of the preliminary work that's been done on it. So that should be landing, I would say, close to the end of the year, probably in a beta.
That's great, Tom. That sounds very interesting. I remember once upon a time we were trying to configure some precipitation for a long historic period, and we'd be patterning gauges, with hourly gauges, but it sounds like, well, obviously there's some newer sources of data nationwide and normalizing tools, but it seems like the days of patterning data might be well assisted by some of the tools that you're developing right now. So that's awesome.
Yeah.
I think, Brett, you gave a lot of great suggestions and thought-provoking ideas on fitting different grid time periods and just kind of considerations and setting some of those parameters to run in normalization tools. But those are all really good to think about when you're working with precipitation data sets or other meteorologic data sets. Any other questions from the field out there? All right, well, this has been a very informative presentation. Garrett and Brett, thank you for all of your time in preparing the presentation. I think it'll be really useful for us moving forward, and I know as you get involved in projects, we can think back to this great presentation, and we'll have the materials to reopen and review and play back again. So thank you for that. Thanks for being willing to share with us.
Yeah, and there's just a list of people at HEC in the St. Paul district that either helped in some capacity with the development, writing the tutorials, or reviewing the tutorials before they were actually published to the HEC's website. And just special thanks to all the people who helped out, because the tutorials ended up being really good and really helpful.
HEC, any other comments on, a lot of the tutorials are now on your website from other presentations as well. And I think we find those as being really great resources to use as a community.
Yeah, I think we should thank MRGMP program, because I think that was the funding source that we used to do all of this. And then with that, thanks to the St. Paul district for helping out with all of the documentation. I know Garrett and Brett said they're on the HEC website. They didn't say that they were the ones who actually developed them. And then I think a host of others probably reviewed them there. So just thanks for all your help on doing that. And they're really great tutorials and guides for folks that want a little bit more information. So thanks all of you.
Awesome. Well, on behalf of our sub-COP, thanks for attending today. Have a good rest of your day, and thanks again for joining us.